A parallel plate capacitor consists of two metal plates, each of area A and separated by a distance d. When the plates of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q, and the other is given an excess charge minus Q. Due to this, a uniform electric field is created between the plates of the capacitors. Towards the edges of the plates, we observe fringing in the electric field. That is, the field is non-uniform when the plates of the capacitor are separated by some distance. We know that d is the distance between the plates. But if d square is very less compared to the value of the area A, the fringing effects can be neglected in the regions which are far off from the edges of the plates. Let the magnitude of the charge density be sigma for the plates with a charge Q on them. Then, sigma is equal to Q by A. Let this be equation 1. Let us assume the region on the left side of the capacitor as region 1, region between the plates as region 2, and the region to the right side of the capacitor as region 3. Let us now calculate the electric field in the regions 1, 2 and 3 with respect to the capacitor. We do this by applying the Gauss Law to calculate the electric field in the regions 1, 2 and 3. We know that for a uniformly charged plane sheet of charge, the electric field strength E at some distance away from it is equal to sigma by 2 epsilon naught. Let this be equation 2. We use this result to calculate the net electric field strength in regions 1, 2 and 3. In region 1, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the left. We also see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the right. Hence, in region 1, the net electric field strength E naught is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0, since the two electric fields are oppositely directed. Now let us look at the region 3. In the region 3, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. We see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the left. Hence, in the region 3, the net electric field strength is equal to plus sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0. Since the two electric fields are oppositely directed in region 3 as well. Now let us look at region 2 between the plates of the capacitor. In region 2, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. We also see that due to the negative plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the right. The region 2, which is in between the plates, has two electric fields of equal magnitude, sigma by 2 epsilon naught, which are both pointing towards the right. Hence, in the region 2, the net electric field strength E naught is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. On simplification, we get E naught is equal to sigma by epsilon naught. Let this be equation 3. Let the potential difference between the positive and the negative plates be equal to V. For a uniform electric field of strength E between the plates of the capacitor, we have V is equal to E naught D. Let this be equation 4. Substituting equation 3 in 4, we get V is equal to sigma D by epsilon naught. But we know that the charge density sigma is equal to Q by A. Therefore, we have V is equal to QD by A epsilon naught. Let this be equation 5. Now, capacitance of a parallel plate capacitor C is equal to Q by V. Let this be equation 6. Substituting equation 5 in 6 and simplifying, we get capacitance C is equal to epsilon naught A by D. Let this be equation 7. This expression for the capacitance shows that the capacitance is directly proportional to the area of the plates A. And inversely proportional to the distance between the plates. We know that the capacitance of a capacitor not only depends on the geometry of the plates, the distance between the plates, but also depends on the dielectric medium between the plates. When there is no medium between the plates, let the potential difference between the plates be V naught. The electric field strength be E naught, and let its capacitance be C naught. We know that the capacitance C naught is equal to Q by V naught. Let this be equation 8. The electric field strength E naught is equal to sigma by epsilon naught. Let this be equation 9. The capacitance C naught is equal to epsilon naught A by D. Let this be equation 10.